So I wanted to post a video that went over the basics of nodal analysis, as well as define my sign convention as utilized in the worked examples, which are posted on the course website. So recall in nodal analysis, sometimes called node voltage analysis, what we seek to do is write a linear system of equations with the unknowns corresponding to what we call nodal voltages, which we'll define in a minute, from which, given the solution, those nodal voltages, we can determine any circuit quantity that we want. So the first step in nodal analysis is to identify what are referred to as essential nodes. And essential nodes, by definition, are simply any node at which three or more components are connected. So if you kind of go around the circuit, you'll notice that this specific node, maybe we'll call that node A. We have the interconnection of three components, the 1 amp source, the 2 ohm resistor, and the 6 ohm resistor. In a similar fashion, at this particular interconnection in the topology, say node B, we have the interconnection of three components, so by definition that's an essential node. And in a similar fashion, at this node, that corresponds to the interconnection of four components, the two sources and two of the three resistors. I'll call that C. So I have three essential nodes corresponding to the set. I was getting ahead of myself there. I wrote A, and what I meant there to do is to say that I've denoted my three essential nodes as the set A, B, and C. Recall that in nodal analysis, the next thing that I want to do is identify a reference node. So I'll define my reference node as being node C. That's typically the convention that you see employed within circuit text and whatnot. I'll denote my reference by the ground symbol. Once I've done that, the next thing that I need to do is write a linear equation for each of my essential nodes, besides the reference, of course. And that equation, of course, is based upon enforcing Kirchhoff's current law. So if I look at node A, for example, you'll notice that the current in one of the branches out of node A is already defined. Particularly, we know that from the left branch, the source forces a current of 1 amp into the node. So rather than define an arbitrary current there, say I1, and just simply by observation set that equal to what would be -1, I'll just avoid that altogether, and I'll only define current variables in the case at which I don't know the currents. So clearly, I don't know the current through the 2 ohm resistor, so I'll define that as I2. I don't know the current through the 6 ohm resistor, so I'll define that as I6. Now this gets to my sign convention. If you notice for that essential node A, I've defined my two unknown currents as emanating out or flowing out of the node. You can do it any way you want. You can have them flowing in, you can mix them up as long as you're consistent, but you're less likely to make mistakes if you employ a consistent strategy. So from those definitions, moving on to node B, notice that there's only one current which we don't know or haven't defined thus far. Clearly in the rightmost branch we have the source current which we know. Coming into node B from the left, we have I6, which we've already defined. Therefore, we need only define one additional current corresponding to the 7 ohm resistor. And again, I'll assume by convention that it flows outwards, so I'll have it going down. So once I've made those parameter definitions, I can enforce Kirchhoff's current law at the two essential nodes. So by definition, enforcing KCL at A, what I find is that the current out equals the current in. In terms of my representation, that would be I2 plus I6 equals 1. And by similar enforcement at B, I can find, again, that the current out equals the current in. That would be I7 plus 4 equals I6. So for the third step, the next thing that we want to do is express each of those unknown currents emanating out of a node, say I sub j, in terms of the nodal voltages, which I'll denote as VA and VB. Now you may be curious how to do that, particularly if it's been a while since you've seen this, or if maybe you're not an electrical engineer by training. Of course, you recall that the basic relationship between voltage and current in a resistor is Ohm's law. So rather than express initially in terms of the node voltages, you could define actual potential differences across each of these resistors. V2, say there. I'll write V6 way above. And then, of course, V7. Right? So from those potential differences across the resistors, it's fairly easy to express each of those currents, which we defined in the previous set, I2, I6, and I7, in terms of those potential differences. So I2, of course, would just be V2 divided by 2. I6 would, of course, just be V6 divided by 6. That would be equal to 1. And in the second equation, I7 would be V7 divided by 7 plus 4 equals I6, which is just V6 divided by 6. So notice that in either case, we haven't really made any substantial progress mathematically. And what I mean by that is we have two linear equations in terms of three unknowns in both this scenario as well as that scenario. So clearly that won't allow us to solve for the unknowns given that information. So now what we want to do is recast these two V6 and V7 in terms of the nodal voltages VA and VB. So we're going to move from three unknowns to two unknowns. And that's going to be a pretty trivial process in the sense that we can relate the nodal voltages by definition to those potential drops. V2 can be expanded as the nodal potential at the positive terminal, which would be VA, minus the nodal potential at the negative terminal, that would be VC. But recall, for this particular analysis, we're setting VC as reference, so that's 0. So V2 is simply VA. In a similar fashion, what would V6 be? Well, of course, V6 would be the potential at the positive terminal, VA, minus the potential at the negative terminal, VB. So that's the difference of the two nodal voltages, VA minus VB. And then finally, V7, of course, will simply be VB, again, minus 0, or just VB. So if you take and substitute into those two linear equations that we had previously, you'll get a 2x2 system from which you'll be able to find VA and VB. From there, you'll be able to find all circuit quantities. And in terms of your approach, particularly in this course, for solving that 2x2 system, it's a small enough system that really any of your alternatives are viable, whether you want to use substitution, elimination, or matrix algebra-based techniques such as Cramer's rule.